This
We did
conference
one
will
class
now be
first,
recorded.
like a small hands-on, where we used both matrix keypad and CLCD together. So in the matrix keypad, we were using certain pins, for the rows we were using port B, for the columns we were using, sorry, I said it wrong. So for the rows we were using port D, and for the columns we were using port B. So while having a matrix keypad used, we couldn't use the CLCD in 8-bit mode. So we used it in 4-bit mode. We tried implementing message scrolling on the CLCD. So initially, to start with, it was like we scrolled the message to the right only in the class, and you are asked to scroll it to the left as a part of your homework. I hope you were able to complete scrolling that message to the left as well. So if you press which one, you have to scroll the message to the right, and if you press which two, you have to scroll the message to the left. So that scrolling it to the left was a part of your classwork, and I'm hoping that you have done it. After that, we started with the analog inputs. So generally what happens is your microcontroller cannot work with the analog input provided to it. So whenever you want the analog inputs to be taken care of, you need an intermediate block in between called as ADC, and ADC represents analog to digital converter. So if you want to give an analog input to the microcontroller, because microcontroller cannot work with analog signals, so there has to be an intermediate called ADC, which converts the analog signal into a digital signal. It should represent some digital value. So with respect to ADC, we looked into some of the important terminologies. We saw what is resolution, which is nothing but the width of the ADC register. Then as the resolution increases, the value what you can store inside the register is also increasing. Then we saw step size, the minimum voltage which it takes for a digital value to change by 1 is nothing but the step size. So we noted all the definitions in the previous class. We have a formula to calculate the step size, which is nothing but input range divided by 2 power the resolution. Then we have full scale range, which represents CFSR. So full scale range is the maximum analog voltage which can be converted to a digital value. So the maximum representable digital value for any analog input, full scale range. Then channel is nothing but an interface between the analog input and also the ADC block. So an interface between analog input and the ADC block is nothing but channel. Is my voice breaking? Okay. Vinita, please check with your internet once. So after the channel, we got to know that any ADC, some of the microcontrollers will have a built-in ADC. Some of the microcontrollers should have an ADC connected externally at a pin of the microcontroller. Now, there can be multiple channels available for the built-in ADC block, but ADC can be active with one channel at a time. So it has to take the input, analog input, it has to convert to a digital value, get it stored inside the register. So it can convert only one analog value to a digital value at a time. Hence, there can be only one channel active at a time. After this, we saw acquisition time, which is nothing but the time taken by the ADC to understand the signal. So that is acquisition time. Then time taken by the signal to convert it into a digital value is nothing but conversion time. So these were the terminologies we discussed in the previous class. Now after that, we wanted to implement one particular project, one particular requirement. So out of all the peripherals available on our PICSIM lab board, we have a potentiometer, which is also called as a variable resistor, which is going to give an analog output. So that analog output cannot be directly given as an input to your PIC microcontroller. You need your intermediate block called as the ADC. Now, our microcontroller, the PIC16F877A, comes with its own ADC block. So I can configure this potentiometer. I can take the analog value from this potentiometer, and the ADC is going to convert it into a digital value. Now, if the potentiometer is giving a value greater than 2.5 volts, my requirement is to turn on the LED. If the potentiometer is giving a value lesser than 2.5 volts, I have to turn off the LED. So this was the basic requirement, but you know that microcontroller cannot make decisions looking at the analog input provided like this. It cannot say to turn on the LED when it is saying 2.5 volts. It cannot accept an analog input. So as an intermediate, we need an ADC block. Our PIC16F877E microcontroller ADC is having 10 bits of resolution. It can store any value ranging from 0 to 1023. We first calculated the step size and we calculated the ADC register value. Now for a voltage which is greater than 2.5 volts, the digital value I end up getting is greater than 512. If the potentiometer gives lesser than 2.5 volts, its digital value will be lesser than 512. So depending on this digital value, I have to take necessary actions on the LED. If ADC is giving a digital value greater than 512, I will turn on the LED. If it gives a digital value lesser than 512, it is going to turn off the LED. Any doubts until this? Any doubts still here? Okay. Now let us proceed with the next. So we had to start with the project of implementing this. We already have a template for that. It is not at all like difficult. Let us just configure this. Now when it comes to the ADC block, ours is a 40 pin DIP. So it has 8 channels, but only one channel can be active at a time. After ADC converts it into a digital value, the digital value will be of 10 bits. Okay, whatever digital value I've got, it is of 10 bits. Now, if I scroll down, I will get the list of the registers associated to this ADC block. Okay, so I may have to scroll down a little, and I am in search of the list of registers associated to the ADC block. You can see the list of registers associated to the ADC block. There are several registers. The major are these 4 registers. So let me show them here directly under ADC block. So they are like the major 4 registers. You can see. The ADC module has 4 registers, and the 4 registers are analog to digital result high register, analog to digital result low register, analog to digital control register 0, and analog to digital control register 1. So these are the 4 registers associated to the ADC block. The ADCON 0 register, which is nothing but analog to digital control 0 register, it is showed in register number 11.1. So that is to control the operations of the ADC block. Okay, so that is to control the operation of the ADC block. Then the ADCON 1 register, so there is one more register called analog to digital control register 1. So this ADCON 1 register, which is showed in figure 11.2, I'll discuss it later. So that is to configure the functions of the port pins. Okay, that is to configure the functions of the port pins. Apart from that, the port pins can be configured as analog inputs or as digital input output. Now, if you see, the analog inputs will be represented as AN0, AN1, AN2. So I can show you in the block diagram. Let me move to the block diagram of the PIC microcontroller. One second. Okay, so this is 873A, then this is 877A. Now, whatever AN0, AN1, AN2, AN3 you are observing, that is nothing but analog input 0, analog input 1, analog input 2, analog input 3. So they represent analog inputs. Now, you can either configure them as analog input, that is nothing but channel, or you can configure them as port pins. Okay, you can configure them as port pins for the digital input output purpose. Let me highlight the 8 analog input output pins. This is first one, second one, third one, fourth one. So here is fifth one. And if you scroll down, here is sixth one, this is seventh one, this is eighth one. So these are the pins which are responsible for acting as analog input output channels. So those, if you're not using the ADC block, can be configured for digital input output. Okay, so that is what the point says there with respect to the ADC block. Okay, I missed that. Let me move to the ADC block. Okay, so that is what it says here. The port pin can be configured as analog input or as a digital input output. It can either serve as an analog input, but in case of digital, it can act as an input output. You are going to set the direction with the help of the tris register in that case. Anyways, as of now, we are discussing about the channel. So we will consider it as analog input taking pins. Now we have to configure two registers, ADCON 0 and ADCON 1. So they are the control registers. And ADRESH, ADRESL are the registers which are used to store the digital value what ADC converts. Now, what is the digital value ADC is going to give is, it's a 10-bit digital value. Can I store the 10-bit digital value inside a single register? Can I store 10-bit value inside a single register? No. Ours is a 8-bit microcontroller and each register can store a maximum of 8 bits. Now, if I want 10 bits to be stored, I have to make use of two registers. So I'm going to make use of analog to digital result high register and analog to digital result low register. Now, how to make use of this, we will see it in some time. So I have to configure two control registers, ADCON 0 and ADCON 1. Now, before I start, let me open the template for this. I'm going to close this project and open a new project. So here under ADC sources, I can get single channel detection program. So first to start with, I'll go with the main function. Okay, so I'm showing you the main function here. To start with the main function, I have init config function. So control comes here in the init config function. Now I have LED array is equal to, is off. So initially I'm keeping all the LEDs off. So LED array is nothing but let's say, let me open. I can use port B or port D. So I'm using port D. So LED array is equal to off is nothing but I'm writing port D with the value 0. So just to make sure all the LEDs initially are turned off. Then I'm setting the direction for the port. So I have to write tris D with the value 0x00. So because it is LED, I have to treat it as output. Then I have to do the initialization of the ADC block, which is written in a separate .c file. Now, what is that initialization to be followed? We will see here. To start with, it has to be control register 0. So I'm going with control register 0. So this control register 0 is having 8 bits starting from bit number 7 to bit number 0. All the bits except this one bit is having readable as well as writable permission, and they are initially returned with the value 0. Now let us start with the configuration from bit number 7. First, I have ADC S1 and ADC S0. Both ADC S1 and ADC S0 is to select the conversion clock rate. Okay, so both ADC S1 and ADC S0 is to select the conversion rate. So first of all, higher the frequency, smaller is the time. Smaller the frequency, higher is the time. Okay, so frequency is inversely proportional to time. I hope you know that. So smaller the frequency, higher is the time it takes. Higher is the frequency, smaller the time it takes. Now, out of all of these options I have got, I am supposed to choose in such a way that conversion is happening as fast as possible. So I have to look at something which is having higher frequency. So higher frequency can be obtained only by F oscillating frequency divided by 2. Okay, so it is F oscillating frequency divided by 2. You have few options of FRC, which is a clock derived from the internal ADC RC oscillator. So this will have a fixed frequency. It will not I will not be able to scale the frequency. So I want to choose higher the frequency so that time occupied is less. So higher frequency will only be obtained by F oscillating frequency divided by 2. And to have this frequency selected, ADC S1 and ADC S0 should be returned with the value 0 and 0. Now to select this frequency, I should also use a bit which belongs to the ADCON 1 register. I will speak about this bit when I go to the ADCON 1 register. As of now, I am in ADCON 0 register. To achieve F oscillating frequency divided by 2, ADC S1 and ADC S0 has to be returned with 0 and 0. By default, they already have 0 and 0 written. Should I do it again? Should I again write ADC S1 with 0 and ADC S0 with 0? That is not required. Divided by 8, see, that is F oscillating frequency divided by 2. So that is the range of frequency you can give. So F oscillating frequency divided by 2, let's say it is 20 megahertz is the oscillating frequency. Divided by 2 is 10 megahertz. Okay. So now if it is 10 megahertz, the time it takes is 1 divided by 10. So that is maybe 0.1 microseconds it takes to do the conversion. Then if you take F oscillating frequency divided by 8, it is 20 mega divided by 8. So it is the rate what the ADC is offering. So 20 megahertz divided by 8, let's say approximately 2.5. Okay. So 2.5 megahertz is the frequency. So time will be 1 divided by 2.5 microseconds. So it will comparatively take more time when it is compared to the top 0.1 microsecond. So I have to choose larger frequency out of all of these options. It is available only for F oscillating frequency divided by 2. Hence ADCON 0 registers first 2 bit has to be returned with the value 0. Got it? Conversion rate, or I would say the time of conversion. Okay. So time of conversion, the time ADC takes to convert the analog value to a digital value is the conversion time. Okay, divided by 2 power n is what ADC is offering. Generally, it will be like 2 itself. Even if you see the scaling of timers, you will get 1 is to 2, 1 is to 4, 1 is to 8, 1 is to 16. Generally, it is very rare you get 1 is to 3, 1 is to 5, 1 is to 7 and all. So generally, whatever rates or whatever frequency you deal with, it will mostly be with 2 power series itself. Okay. Next, I have to choose the channel in which the potentiometer has been connected. Now see, I'm going to make use of a potentiometer which should be converting which gives me a variable voltage, and that voltage should be given to the ADC to convert it into a digital value. Now in order to do this, our board has two potentiometers. I can use any one of them. How to know to which channel these potentiometers are connected? How to know to which channels these potentiometers are connected? What should I refer for that? Yes, I have to refer the schematic. So I'm going to tools, I'm clicking on board, and I'm going to open the schematic of the SPIC microcontroller board. So this is the board and it's the schematic. So I'm going to find for potentiometer. Okay, so P1, P2 will be displayed generally for potentiometer. Okay, so you can see here, there is one potentiometer P1, another potentiometer P2. Now to which analog channel P1 is connected? It should have been AN0 and AN1. It is not ANA0, ANA1. It should have been AN0, AN1. So to which analog channel potentiometer 1 is connected? It is to AN0 and potentiometer 2 is connected to AN1. Now I want to make use of potentiometer 1 for my operation, which is connected to AN0. So I have to specify, I'm going to make use of channel 0 for the operation. So I have multiple channels. Channel 0, this is channel 1, this is channel 2, this is channel 3, channel 4. Then channel 5 is in, okay, this was not the pin. Okay, here. So channel 0, channel 1, channel 2, channel 3, channel 4, then channel 5, channel 6, channel 7. So I have to tell to which channel the analog output providing device is connected. So to this channel, a potentiometer is connected. Okay, pot is connected to this channel, potentiometer 1. So this potentiometer gives me a analog value. The channel AN0 is having ADC. So there is ADC like this. And I'm going to establish the connection between ADC and potentiometer via the channel 0. So whatever analog value this potentiometer gives, it will be treated as an input by the ADC, and ADC gets it converted to a digital value. So I have to tell that whatever input ADC need should be taken from analog channel 0. For channel 0, if you see, I should be writing it with, for channel 0, you can see, I have to write CHS2 to CHS0 with the value 0, 0, 0. Okay, only one channel can be active at a time. As of now, I'm using only one peripheral connected to analog channel 0. To indicate that, please take the analog input from channel 0. I have to write CHS2 to CHS0 with the value 0, 0, 0. So this has to be written with 0. Then this is 0. This is 0. Now initially I already have it written with the value 0. Do you think I have to overwrite it again? Should I overwrite it again? No, that is not required. Next, the next bit is go/not of done bit. It is the analog to digital conversion status register. So when AD on is equal to 1, so AD on is a special bit which is used to turn on the ADC block. So I have to turn on the ADC block. So AD on has to be written with the value 1 to turn it on. AD on should be written with the value 0 to turn it off. Now once the ADC block is on, this go slash not of done bit will represent the status of conversion. If this bit is having the value 1, the ADC conversion is still in progress. And if this bit is having the value 0, the ADC conversion is not in progress. Okay, if a go slash not of done is having the value 1, so you are going to say that the conversion is done. You can get the digital value. If go slash not of done is written with the value 0, so it says conversion is in progress. So that conversion we will see it later. Anyways, I have to turn on the analog to digital converter. What should I write with the add-on bit? Yes, so I have to have it returned with the value 1. So that is the first step we have made here. Add on return with the value 1. This is to start the ADC module. After that, one more thing. I have to configure addCon1 register also. It's again a 8-bit register where 2 bits are unimplemented. Rest of the bits are readable as well as writable, and they are having the initial value as 0. Now I'll come to the ADFM later. First, let me speak about ADCS2. So that's a bit which contributes to the clock conversion rate. So we wrote 0 and 0 already to ADCS1 and ADCS0. I also have to write a 0 to ADCS2. But anyways, it is already 0. I'm not going to overwrite. Then this PCFG3 and PCFG0 from here to here, the 4 bits are used to say analog to digital port configuration control bits. Whether you want all of the analog to digital converting channel to be treated as analog, or you want to refer to some other value, whether you want to see it as a digital pin or you want to use it for reference, you can specify. Okay, if you see the block diagram, ANA3 can act as analog input to the ADC, or it can also act as VREF. So if you look at ANA for other pins, they can act as analog pins. They also can act as digital pins. Now, how do you want to use them? Should be specified by using PCFG3 to PCFG0. As of now, because I'm using only ADC block, let me keep all of them as analog. So according to your requirement, you can make it. As of now, let me make it all of them as analog. So to say all of them are analog, all the pins PCFG3 to PCFG0 should be returned with 0, 0, 0, 0. So this is a 0, this is a 0, this is a 0, this is a 0. So again, initial values are already 0, so I'm not going to overwrite it. Are you able to follow this? There is only the Ninja responding. What about others? You don't have to configure 4 registers. You are supposed to configure only 2 control registers. So the address, ADRESH and ADRESL. So that is to store the digital value. 2 registers are to store the digital value. Only 2 registers are used to configure the ADC block. Okay. Now one last is ADFM. It's the bit which says in what format you can select you can store the data. See, ours is a 10-bit resolution ADC block. Once the analog value is converted to a digital value, it gives a 10-bit big digital value. That 10-bit big digital value cannot be stored inside a single register. I need two registers. One is high register, the other one is low register. Now, how are these 10 bits stored in the high register and low register is, we have something called as justification. Okay, so result justification. So ADC takes the analog input, it converts it to a digital value which is of 10 bits. Okay, it converts it into a digital value which is of 10 bits. Now, how are these 10 bits stored is, if ADFM is equal to 1, I have selected right justification. If ADFM is 0, I have selected left justification. Now, what happens in the right justification? Assume the 10-bit value I have ended up getting is 1011111010. So just a random output. Assume after taking the analog input, ADC is giving me this 10-bit digital value. So this is representing some value varying from 0 to 1024. Okay, it should be representing me some value varying from 0 to 1024. Now, if it is right justification, okay, let me highlight here. So if it is right justification, remember the lower 8 bits will be stored in the low register and upper MSB bit will be stored in the LSB of the high register. Okay, so low register will have 1, 1, 1, 1, 1, 0, 1, 0. So that is what you get in the low register. In the high register, the two MSBs will be stored in the LSB part, that is 0, 1. The remaining will be added with zeros to the left. So this is how 10 bits data is stored in two registers when it is right justification. Similarly, when it is left justification, the 8 MSBs will be stored in high register. 2 LSBs will be stored in MSB of low register. So it will be 0, 1, 1, 1, 1, 1, 1, 0. Okay, so that is high register. Then in the low register, 2 LSBs will be stored in the MSB. 1 0 will be stored here. Remaining 6 bits will be added with 0. So this way, whatever 10-bit value is there will be either stored as a right justification or it will be stored as a left justification. So ADFM with 1 is right justification. ADFM with 0 is the left justification. So in our project, we have taken ADFM return with the value 1. That is right justification. And that is the initialization of the ADC block. Clear? Okay. Now, the ADC block is connected to the potentiometer 1. The first potentiometer is connected to the AN0 of the ADC block. Now, you have told the ADC, please take the input from ANA0 and convert it into a digital value. So, this ADC will take the input from AN0, which is having a potentiometer connected. It converts it into a digital value and stores it into the two registers, register high and result high and result low register. Now to fetch that, I have a function return called read ADC. I have to fetch that. So I have a function called read ADC return. Now what happens in the read ADC is, first of all, you know that there is acquisition time, there is conversion time. You have to let some time given to the ADC block to have the conversion done. Now what we do in the read ADC block is, I'm going to tell the ADC to start conversion by having go with the value 1. Okay. So when I have go with the value 1 return, I'm going to start the conversion. The moment n done falls down to 0, the conversion is completed. So I am waiting till conversion is completed with the help of a while loop. This is again a blocking statement. Until n done falls down to 0, I'm waiting with the help of a while loop. The moment n done falls down to 0, you come out of the while loop and it is understood that the conversion of the data is done. Okay, so the conversion of the data is done. Now what happens after this is, the data is converted. We have got the write justification. So according to write justification, 8 MSBs are returned, 8 LSBs are returned to the low register. 2 MSBs are returned to the LSB of the high register. Now I have to frame a 10-bit value. It is something like this. So this is the 10-bit value I have got and it is written in the 2 registers. I have to combine this to get one 10-bit value because it is written in 2 separate registers. So I cannot directly do ADRESH or with ADRESL. Okay, that is not possible. So in that case, I'm merging the 2. I'm not combining the 2. Okay. So what I have to do is, ADRESL is already there. This ADRESH should get shifted to 8 position. So it is something like this. This is ADRESH. This is ADRESL. ADRESH is having let's say 00000001 and ADRESL is having 11111010. Okay, so that is ADRESL. Now these two should come to this position somewhere here. So I'm going to shift it to the left for 8 times. Okay, this I'm going to shift to the left for 8 times. After I shift it to the left for 8 times, there will be 0, 1, 0, 0, 0, 0, 0, 0, 0, 0. That if I OR with, okay, so that if I OR with 1, 1, 1, 1, 1, 0, 1, 0, don't you think I end up getting the whole 10-bit value at once? 0, 1 here, then 1, 1, 1, 1, 1, 0, 1, 0. Don't you think I get the 10-bit value? Yes. So I have to get the 10-bit value. So that is what we have done here, here in the project. I'm doing ADRESH left shifted for 8 times or with ADRESL. The data will be in the left. No, it is write justification. ADFM is written with the value 1. It's write justification. Go is set by us, then end done is set by whom and where. So go will be set by the user to start the conversion, and end done will be returned with 0 by the microcontroller, the ADC block. So end done is a bit which will be returned with the value 0, the same bit. The same bit you can either refer it as go or you can refer with end done. So to start the conversion, we have to write it with the value 1. And to stop, to know whether the conversion is done or not, I have to wait till end done falls down to 0. So end done will be returned to 0 by the ADC block once the conversion is done. Okay. So that register value, the 10-bit register value is made as a whole number that is returned. So I collect that into ADC register value variable. Then I'm calling glow LED function by passing ADC register value. Now, if ADC register value is greater than or equal to 512, LED 1 is turned on, and if ADC register value is not greater than or equal to 12, so LED 1 will be turned off. Okay, so this is the project we have done. So let me build this and show you the output. Okay, so build has been successful and loading is also completed. So I'm going here to load the hex file, then load hex. Under AN template code, then ADC sources, then single channel, distribute, default, production, the hex file. There was a doubt, let me read. Where we configured AN0, we said it here with the help of the bits. Let me show that here. So AN0 I specified by having CHS2 to CHS0 return with the value 000. By default, they were anyway 0, so I didn't make any change. Okay, fine. So you can observe the output here. So I have configured the first potentiometer. To increase the voltage, you have to move it to the right. To decrease the voltage, you have to move it to the left. Okay. So I'm increasing the voltage as of now. I think it is lesser than 2.5 volts, which is why the digital value you have got is lesser than 512. So port D LED is not turned on. Oh, sorry. So DIP was in the opposite direction. Okay. So it is greater than 512 right now. So because of that, LED is turned on. So I move it clockwise. Okay, you can see I'm moving it clockwise. As I move it clockwise, so this is the maximum actually. At what point it is stopping right now is the maximum, which is representing 5 volts. Its digital value is 1023. Okay, I move to the left, the voltage is decreasing. The corresponding digital value is also decreasing. If it decreases lesser than 512, LED is not turned off. So actually, if I reach the lower, it should not allow me to move after that. But in this case, I can move from 0 volts to 5 volts directly like this. But I hope you are getting this. So this is the maximum point, which is representing 5 volts. And this is the minimum point, which is representing 0 volts. So as the voltage increases, the digital value is also going to increase, and correspondingly, if the digital value is greater than 512, so I am going to have the LED turn on. If the digital value is lesser than 512, I will have LED turned off. Clear with this example? Okay. So if you want, you can note this down. We'll take a break of 2 minutes and continue. Okay, can we proceed? Hmm. Okay, so there's a doubt. As we don't have any sensor, we're giving voltage using potentiometer. If we have sensor, then from the input we get the voltage, right? Yes. So for example, there is a sensor, like if there is any sensor to which the pin is connected. Okay, so like there is a sensor where you have got the analog output being provided. So that sensor can be connected to any of the channel here of the ADC block, and whatever analog output it provides, this ADC is going to consider it as an input and it is going to convert it to a digital value. And how to generate PWM using timer? Can you give one example? Uh, I'll come to that, I think. Okay, let me give a small idea. I'm not supposed to give the hint of the assignments, but anyways, I'm giving you. So if there is a frequency, I'm just giving you a hint. If there is a frequency of 5 hertz, okay. So first you have to calculate the period of each pulse. Okay, you have to calculate the period of each pulse. Then whatever on time off time is there, that you have to achieve with the help of timer. For example, if the on period, okay, so period is 5 hertz, okay, so sorry, frequency is 5 hertz, period is 1 over 5. So how much is 1 over 5? 0.2 milliseconds, right? So if it is 0.2 milliseconds, on period has to be 0. Okay, according to the duty cycle. If assumed duty cycle is 50%. Now for 50% duty cycle, on period has to be 0.1 millisecond and off period has to be 0.1 millisecond. So this on period and off period, the toggling of the pulse should happen in the ISR. You have to calculate this 0.1 millisecond with the help of a timer. You have to count 0.1 millisecond with the help of a timer. So every time after this happens, you have to go to the ISR and you have to toggle the pin, whichever pin you are having the PWM waveform generated. So that pin you have to toggle. So RD0, for example, let's say you are making it as RD0 pin. You want to get a modulated waveform generated at RD0 pin. So after 0.1 milliseconds, RD0 has to be returned with 0. Again, after 0.1 milliseconds, RD0 has to be 1. You have to toggle the RD0 pin in the ISR. For every 0.1 millisecond, control has to go to the ISR and it has to toggle the RD0. I think this is the least hint I can provide. Did you get? Okay, it should be helpful at least. How can we control the brightness of the LED? Okay, so to control the brightness of the LED, you have to, I think we did a classwork also, like a classwork where we tried implementing LED dimmer application. So as I press the switch, I increase the duty cycle and accordingly the voltage delivered across the LED was also increased. And as I press switch 2, I decrease the duty cycle and accordingly I'm going to have the brightness of the LED decrease because I'm providing lesser voltage. And that has to happen on a very swift manner. Okay. All right. So let us proceed. I have one more small program here. Then I can take up your doubts if time permits. But I want to complete this one more program. Now, in this program which you saw, which we did right now, Which channel did we use? Which channel did we use out of the 8 available channels? Which channel did we use? Yes, it was AN0, which is analog channel 0. Now, do you think the same code works if I have an analog input provided at channel 2? Do you think the same code works if I have analog input provided at channel 2? No, that is not possible. It will not work. Okay, so that is not possible. So, what if I want multiple channels to be used in a single program? As of now, in this case, I'm using a single channel. So if you want some other channel, then you have to update it from CHS2 to CHS0. If you want channel 4, CHS2 to CHS0 has to be written with 100. If you want channel 7, CHS2 to CHS0 has to be written with 111. Now, what if I want multiple channels to be used in the same program? If it is a single channel, it is fine. What if I want multiple channels to be used in the same program? Now I'm going to close this project and open another project called multi-channel detection. Now what I will do here is, I have two potentiometers on my board. One potentiometer is connected to analog channel 0. One more potentiometer is connected to analog channel 1. Okay. So I am going to make use of both the channels. So whatever potentiometer 1 is providing, I convert it into a digital value and I display it on the CLCD. Whatever potentiometer 2 is providing, it is connected to channel 1. So I also convert it into a digital value. Then I am going to display that digital value on the CLCD. So I'm going with the main project. You can first initially see I'm doing the initialization of the CLCD. Then I'm doing the initialization of the ADC block. Now initialization of the CLCD is not changing. Initialization of the ADC block is also not changing. Now I have to first say channel 0, then I have to say channel 1 to the ADC block. So you know that there is only one channel which can be active at a time. Only one channel can be active at a time. So first I have to take the input from channel 0, convert it into a digital value. Then I have to take the input from channel 1, convert it into a digital value. Now to have channel 0 set, I should write CHS2 to CHS0 with the value 000. For channel 1, it is 001. For channel 2, it is 002. For channel 3, it is 011. So I am having the channel value. So that value I have taken it as a macro return here in the ADC.h file. So channel 0 represents 0x00 means 001. Channel 1 represents 0x01 means 001. Channel 2 represents 010 means hexadecimal is 0x02. Channel 3 represents 011. So its hexadecimal equivalent is 0x03. So like this you can write it for all 8 channels. Now I'm taking two variables, ADC register value 1 to collect the register value of ADC after you convert the analog input of potentiometer 1. ADC register value 2 is used to collect the register value of the ADC after you convert the analog output of potentiometer 2 to a digital value. Now first I want to convert the analog input of potentiometer 1 to a digital value. Potentiometer 1 is connected to channel 0. So I am passing channel 0 macro as an argument to the read ADC function. Now what happens in the read ADC function is, first I have to specify my channel. I have to specify my channel value to CH2, CHS1 and CHS0. Okay. So, first, whatever is my channel value, I have to bring it to the fifth, this is third, fourth, fifth position. Whatever is my channel value, I have to bring it to fifth, fourth and third position. How to do it? Whatever is my channel value, I want to bring it to fifth, fourth and third position. So what should I do? So channel 0 is representing 0, 0, 0. To bring it to fifth, fourth and third position, I am going to left shift it for 3 times. So whatever value is there, it will come to the fifth, fourth and third position. Correct? Now after that, I have to add it to the fifth, fourth and third position of add con register. First of all, I don't know what is there in the fifth, fourth and third position. I have to clear that. So to clear, I'm going to say add con 0 and with 0x 1100 is 1100. It is C. Default it is 0, but later I might change. No. So I have to update channel every time. So I'm taking it as 0xc, then 0111, 7. Okay. So 0xc7. Now when I add con 0 with 0xc7, it is actually clearing the fifth, fourth and third position of the add con 0 register. Then whatever is the channel 0 value, I'm left shifting it for 3 times, I'm ORing. Now after I perform this operation, YC7, so I have to AND with 1, 1, 0, 0, 0, 1, 1, 1. Only these 3 bits I have to clear. Rest of the bits have to be remaining as it is. So I am ANDing with 1, 1, 0, 0, 0, 1, 1, 1. So 0xc7. Now after I perform this operation, 0, 0, 0 gets returned to CHS2 to CHS0. Now I told the ADC, take the input from channel 0, convert it into a digital value. So it will be converted to the digital value. Okay. After I do go with 1 and wait till end on falls down to 0, it will be converted to a digital value and it will be returned in the result low and result high register. I collect that value and I return that value to the main function. That will be received by ADC register value 1. Next, I have read ADC function called by passing channel 1. So this time I am telling, take the input from channel 1, convert it into a digital value and give me the digital value. So I am specifying channel 1. Okay. So when I do this, channel 1 gets returned to the register. So after I perform this operation, channel 1 represents 001. So 001 gets returned to the CHS2 to CHS0. Okay. So 001 gets returned. Now once 001 is returned, ADC will understand that it has to take the input from channel 1. So I have potentiometer 2 connected in channel 1. So that it converts to a digital value, stores it into the same low and high register. I merge it to form one 10-bit value and I return it, which will be collected by ADC register value 2. So now ADC register value 1 is having the digital value of first potentiometer. ADC register value 2 is having the digital value of the second potentiometer. Are you able to follow this? Now I have to display it on the screen. So to display it on the CLCD, I'm calling display function by passing ADC register value 1 and ADC register value 2. What type of values are these? What is the data type of the values of these registers? It is integer. Can I display integer directly on the CLCD? Can I display integer directly on the CLCD? No, I have to convert to individual characters. So you can see here, I have taken a character buffer of size 5. Now assume ADC register value 1 is having some 1023. Okay, the digital value 1023. Now I have taken buffer array of size 5. I is a variable return started with the value 3. So what I have to do is, this buffer of I should have, assume ADC register value is 1023. So I have to store 1, 0, 2, 3 as characters into the buffer array. First ADC register value mod by 10 gives me integer 3. To that if I add 0, it will give me character 3. I'm writing into buffer of 3. Then ADC register value divided by 2 will have 102. It's a do while loop, so I minus minus. I is 2 this time. Then 102 mod by 10 will give me integer 2, plus 0 will make it character 2. That character 2 is stored in buffer of 2, and I'm doing ADC register value of 1 divided by 10. It will make it 10. So that way I'm converting the integer into individual characters. I'm storing it into the array called buffer, and buffer of 4 is terminated with a null character. Then I'm calling CLCD print function for printing buffer on line to third position. Then I'm writing C1 channel 1 on line to ninth position. I'm converting the second digital value, which is stored in ADC register value 2, into individual characters. I'm storing it in the same buffer and I'm displaying this. So this is not at all something which breaks your head. It is very simple. It is only converting the integer value to individual characters, and it is storing inside a array, which is an array of characters. And I'm displaying all of that at once. Okay. Let me load the hex file for this project. Once you see the output, you will be able to understand it. Distribute, default, production, the hex file. You can see first line I have ADC test printed, second line channel 0. So whatever input ADC takes from channel 0, it is converted to a digital value, and that digital value is displayed on the CLCD. Whatever input ADC takes from channel 1, that is converted to a digital value, and that is displayed on the CLCD. You can observe here, I am rotating clockwise. Okay, so you can see the maximum 1024. Okay, this is maximum 1024 for channel, 1023 only. So if you move it in the anti-clockwise direction, it is going to reduce. Okay, so you can see anti-clockwise direction. So clockwise, if I move, it increases, anti-clockwise, it decreases. Similarly for channel 1. So if I move it in the anti-clockwise, the digital value is decreasing. Least is 0, maximum is 1023. So you have to move it to the clockwise direction to increase. So you can see this is 1023. So like this, whatever is the analog value your potentiometer is giving, ADC is converting it to a digital value. Clear with this? Everybody, is this clear? Okay. And this completes all the peripherals of the embedded programming. So this completes the chapter embedded programming. And after this, we are supposed to start with communication protocols. Now, before I start communication protocols, have you got any doubts? So you were asking for a doubt clearing session. I asked you like to have your doubts kept. I hope you are able to give. After taking one channel input and completing then we are taking the input from the second channel, right? Yes. How it can first channel input taking completed and only two channels you showed, maximum two channels we can see. So there are 8 channels. Okay, as of now I have only two analog output providing devices, that is potentiometer 1 and potentiometer 2. So you can have potential if you have multiple other analog output providing devices. You can get it connected to different other channels of the ADC. You can convert that to a digital value as well. So as of now, because I had only two potentiometers which has an analog output providing device, I showed you only two channels. So there are 8 channels in total. You can switch between any channels. How it can know first channel input taking completed so that I can start second channel. You're doing it no here in the program. So when you are converting, if you observe here in adc.c, here you are taking the input, you are waiting till the conversion is done. Only after the conversion is done, you are coming out of the read ADC function. So you will collect the digital value into a variable. Then if you switch to another channel, you will again wait till the conversion is done to a digital value. You collect it. So you are not like moving in between itself. You are not switching between the channels in between itself. Only after you are done converting, you come out. Then again you call the function to switch to another channel. Are you getting this? Okay. Meanwhile, what about others? Have you got any doubts? Can you show on board other channels of ADC? I can show it here. Like I don't have a peripheral connected to the other channels of ADC. Okay. Yeah. This is ADC. So I have only two potentiometers connected to the two channels of the ADC. Someone's mic is on. Please check with your mic, guys, once. Okay, I've muted. Okay, so I have only two potentiometers. Apart from that, I think there is a temperature sensor. Let me find for it. These are all displays. Okay, so here it's a temperature sensor. It is being connected to temp. Okay, so if you search for temp, so actually you can configure, you can get it connected to any of a analog channel. Okay, you can get it connected to any channel, so that you have to read the data sheet of the temperature sensor. So apart from that, I don't think any other peripheral has been connected to the analog channel here. So we have ADC, we have RS-232, we have external EEPROM. So they are all not connected to any of the other analog, they are not analog output providing devices. So I hardly have two potentiometers as of now and one temperature sensor which can be connected to any of a analog channel. Okay. If we connect sensors externally, that is not because it's a simulator board where the connection is already made. You cannot have another connection established. Like, you cannot create a connection. If you are dealing with your own board in the hardware, yes. If you have your own microcontroller, if you are using a breadboard, then you can have a sensor's output pin connected to one of the analog channel. So that is possible. Okay. From yes, from AN0 to AN7, wherever you want, you can have the sensor connected. How can we configure a buzzer? Okay, so buzzer is like a very basic, let's say, peripheral. Okay, so when it comes to the buzzer, so it's like a peripheral which has been uh, like making a sound. Okay, but it's like a indication. It is one of a feedback device. So you just have to find where the buzzer is connected, to which pin the buzzer is connected, and you just have to provide the output. Okay, so here, hmm, okay, so what you have to do is, a buzzer is like a simple, it's a kind of an LED. Okay, so one pin, it will be like this, there will be a buzzer. So this pin will be connected to some pin of a microcontroller. Let's say RA1 or RA2, something like this. Okay. So what happens in this case is, you can actually, you have to do a comparison first of all to turn on the buzzer. So for example, let's say you take a temperature sensor, so you have to convert it into a digital value. So that digital value, if it is, let's say, greater than some predefined threshold value, you have to provide one to this particular pin of the microcontroller that will just turn on the buzzer. So 1 provided will turn on the buzzer, 0 provided will be turn offing the buzzer. The only thing is you have to see when to turn it on, when to turn it off. So for that you need a situation when potentiometer is giving some voltage, you want to turn on the buzzer. When temperature sensor is giving some temperature, you want to turn on the buzzer. So you need a comparison for that. Apart from that, buzzers are as simple as your LED. There is gamepad with analog output in the spare parts. I have not explored it yet. Like in the spare parts, you can see many of the things. Like there is, yeah, analog gamepad. There is a temperature sensor called FM50. Then I have few more potentiometers if you want. Then you have rotatory potentiometers and scaling potentiometers. Then push buttons which work according to the analog output. So this way you can like, gamepad here is a input device which is used to provide an input to the microcontroller as an analog value. So this you can have its output connected to let's say channel of a ADC, convert it into a digital value and use it. I'm not aware of how this gamepad works. Like, you can try exploring if you get time. You can try for potentiometers anyways. So potentiometers are there. You can have push buttons which gives you an analog output. So you just can explore any of them. The only thing is, you should get its output connected to a particular pin of the microcontroller. So where a analog channel is available. Okay, you can see few potentiometers here. I can connect it to some channel. So let's say AN2. So that is where one of the analog channel is available. Then you can increase, you can decrease. So that you can do. You can read, you can make configurations. So if you want, you want me to show that one more potentiometer. I think you can do it on your own. It's not very difficult. So you just have to update with channel 3 here. So, uh, sorry, channel 0, channel 1 I have, channel 2. If you take, so that has a potentiometer which I have just connected. So that digital value you can display it on the CLCD. Okay. Any other things? Hmm. How, how can we got to know a pin is time multiplexed or frequency multiplexed? Uh, like why is it necessary to know how is it being multiplexed? Is there any particular reason for it? I'm not sure how to identify whether it is time multiplexed or frequency multiplexed. The only thing I can say is they are always a bidirectional pin. They can make changes. You can treat it as an input, you can treat it as an output. So, like time multiplexed or see, both of them are almost the same, right? So, time is inversely proportional to frequency. So I'm not very sure how it works, but if you want me to say that, I can say it in tomorrow's class. How can we get to know whether the pin is time multiplexed or frequency multiplexed? So I'm going to note the question down. I don't know about it yet. Okay. So I kept error of one pic in WhatsApp. Please see, ma'am. I added header file also. Error use of undefined identifier trsd expanded from the macro. Uh, SSD data port. Okay, Sayed, let me check. I'm really sorry that I'm like literally busy with uh, more classes. I couldn't look into your doubt. So let me check and get back to you after the class gets completed. Okay. Uh, Yeah, Sayed, once class gets over, I'll definitely look into the question. Which technique is used in PIC16F877A analog to digital conversion? So, see, because it is data acquisition, okay. So, when it comes to the data acquisition, the very commonly used ADC block will be SAR in case of data acquisition and sigma delta for the voice or audio acquisition. Means conversion of a data, you can go with just the SAR, and when it comes to the Voice or audio, you are going to make use of sigma delta very commonly. So I think it's the SAR which is available. What type of questions are asked in the interviews on peripherals? It can be anything. So it need not be particularly to a peripheral like this. Whatever we have theoretically discussed, they may ask you to do a programming part also. So it's like SAR, I would say successive approximation register. Okay. So like the questions what you can expect in interviews will be like they may ask you to explain how busy flag works in your CLCD, or they may ask you to explain how conversion is happening in ADC block in general. It need not be with respect to the PIC microcontroller itself. It can be regarding anything. Okay, in general, how timers are going to work, or how an interrupt plays an important role with respect to polling. As a disadvantage of polling, how can you use an interrupt? I'm just briefly giving out some questions. It need not be something very same. Okay, something like that. They may ask to explain anything. Okay, any other doubts? And Syed, I think I've lost the, like, I don't know if I have so many chats to be replying about. Can you please ping me up again, like just a message so that I can see your doubt? Okay. Uh, okay, fine. Thank you. Madam, can we use two channels together for ADC's conversion? No. So as we discussed, there can be only one channel active at a time. As there is only one register to collect the output of the ADC block. So if you use two channels, it may give two different digital values. Two different 10-bit digital values, you cannot store it into a single, like you need multiple registers. So because there is only one register, in fact two, a low and a high register, but that can store only one digital value at a time. So there can only be one channel active at a time. Can we connect external ADC to other ports? So if you want, yes, you can. Like if you are using the hardware separately on the breadboard, yes, you can. Okay. Then coming to whether the microcontroller has a DAC block, like you may have to refer the data sheet. Let me search if it has a DAC block available. Okay. There is okay, so it doesn't have a DAC block. You don't have digital to analog converter on your microcontroller, like on the PIC microcontroller. Currently, automotive embedded is in demand due to electric vehicles. What else we should focus on to get cracked? Uh, Automotive interviews. Like you have to be working with every particular peripheral. So you just have to be uh, like definitely every day one or the other trending topics will be in the market. So I would suggest is you to be thorough with the basics. So even if it is an electric vehicle you want to design, an automatic device you want to design, you want to design any of an embedded system, you should have the basic knowledge of how a microcontroller works, how a microprocessor works, how to configure different peripherals. Now that you have a board right now, but tomorrow you may not be given with the board. You have to pick the peripherals, you have to pick the controller, you have to establish the connection, program it. So you just have to have the basic knowledge of programming any of a given microcontroller. So using that, you will definitely be able to adapt to any emerging trend which is happening on every day to day's life. Nagendra is asking, is PCL under embedded? May I know what is PCL you are referring to? Sorry, PLC. Yeah, I found it's programmable logic controller. That's anyways a controller. Okay. Like it is internal controller itself. So yes, you can consider it to have any of an embedded system designed. Okay. Now, if it has only a processor, then it's a microprocessor. Like if it has more than like just a processor, then you can see it as a controller. Ma'am, what embedded system designers actually do in the industry? Like what are the actual assignments or work they do in the industry? So it's like programming a microcontroller itself at the end, whatever embedded engineer do. So he or she may not have to work with only one peripheral at a time. So their task is always to design an embedded system which is new in the market. So you may have to work with multiple peripherals at once, and you may have to work with different controllers. So you cannot be sticking to one particular controller. So there are n number of controllers in the market. You have to know how to read the data sheet, how to program that controller, what are the features available in that controller. So that is what we do, like an embedded engineer do in the industry. Okay. What firmware engineer has to do? Firmware engineer is more of a like a software of dev. Like he may have to write the program to configure. Okay, so he may have to write a software. He may have to write a software for a particular components working. Whatever coding they you do here, embedded coding, that can be done by a firmware engineer also. Yeah, for the drivers, for any given peripheral. So whatever you are doing, in fact, it's a driver itself. You are making the peripheral communicate with your microcontroller. Your microcontroller is communicating back with the peripheral. So at the end, what is happening is always a driver itself, but not a full-fledged driver, because you don't directly go to, let's say, Hmm. You don't directly go to the memory. You don't play directly with the memory. You play with registers, but not directly by yourself. So you can see it as a high-end driver. Yocto. Mm, okay, so according to what I see, I think it's one of a distribution of Linux operating system. So like you have Ubuntu, you have Kubuntu. So Yocto is one of distribution of Linux operating system. So they use like Linux operating system for having the projects designed. Actually, buses, right, we used to connect and communicate. Then what drivers do? Buses are just the hardware to transmit. Okay, address bus or data bus are just the hardwares to transmit your data to and fro. So driver is like a full-fledged program. So a program which it's a software which helps the peripherals communicate with each other or communicate with the controller. Okay, fine. So I'm going to stop here. You can have your attendance marked. So tomorrow we are going to start with the communication protocols. Okay. So please make sure you're joining the session on time. It's really important, a very important topic. Not that the other topics are not important. So very important. We are going to start it from tomorrow's class. Hope the class has all been clear. Thanks for attending today's class. We'll continue tomorrow. Thank you all. Please have your attendance marked before leaving the session. How exactly the hardware is processing the data that we are giving in the hex file. So any controller or any device will be able to understand things only in terms of zeros and ones. So you are giving it in hexadecimal. Internally, there are zeros and ones being represented. Okay. Thank you all. We'll continue tomorrow.